Hi. So this is, I don't know, just some thermodynamics questions, and yeah, let's just go. These are just like 11 questions, and they are sort of interesting. So let's just take a look. So first question is: show that the Helmholtz free energy of a system whose volume is V in contact with a heat path at temperature T is minimum at equilibrium. Um, and then something more. But first, we have to show this thing. So okay, let's just think about it. So you have a system, and the system could contain all sorts of weird things, like it could contain maybe some chemicals which are reacting or whatever you want, and then you have this reservoir at temperature T throughout, and the volume of this system is fixed. So everything's fixed. There's like no motion of any boundaries anywhere, except obviously inside of this box. We don't quite know what's happening. There could be like lots of random stuff happening in there. We have no idea. So what we want to show is that at equilibrium, the Helmholtz energy, which is given as just the energy minus this minus the Ts quantity, well, this guy is not going to change at equilibrium, right? Or more like its minimum, right? The way we will show that is that any process, right, any quasi static process from that equilibrium point should necessarily have its entropy change being positive or equal to 0, right? So um, yeah, and that will like necessarily mean that um, sorry, its entropy change being less than or equal to 0, so like decrease in entropy, or um, it should be equal to 0, and we know that the entropy thing never decreases, so that will sort of show that yeah, this thing is the equilibrium position. Like you cannot in fact move to a position that is better than this, right? But essentially what we want to show, and like yeah, so like you have this phase space, and you have this point which is at equilibrium. Then showing that it's at equilibrium is essentially saying that the entropy of universe is not going to change throughout this guy's surrounding, right? So that's to say that the gradient of entropy with respect to our phase space, so just x vector, that should be equal to 0 at this point. Yeah, now let's just actually try to figure out how are we going to show this. So the only sort of process that we can do is, well, take heat from this reservoir and put that heat into this bucket, into this system, right? Yeah, so since it's a constant volume process, what we can say is that the heat that we take from the reservoir will be exactly equal to the change in energy of this system. So we have the equation dE is uh, the heat input to the process, right? And and um, we know that the entropy change of the surrounding, that will necessarily be so that will in fact be minus dq upon the temperature T. Why is that the case? Because with entropy you have to be sort of careful, but can we actually write this thing that delta S universe is just, so ds universe is essentially just this quantity? Can we actually write it like that? And it turns out that yeah, we can in fact write it like that. The reason is that ds universe is actually equal, sorry, ds, I shouldn't say universe, I should say surrounding. So ds surrounding is just equal to you know dq reverse, so minus dq reversible upon the temperature, right? Or I should just really say uh, positive dq reversible surrounding upon temperature, but that's basically just minus dq reversible upon temperature. Yeah, and we can write that certainly, because that's just a definition of ds, not a definition, but you get it, right? It's a very valid equation. And what this is saying is that if there is a reversible path from this current state of the surrounding to some state which has to the final state, right? If there is a reversible path and it's at temperature T, right? Then you can certainly write it like that. So since this reservoir cannot move or anything, there's no possibility of doing work on it. The only transfer of energy we can do is via heat, right? So the dq value in the reversible or in the irreversible, or in fact in any sort of way, in any process in fact involving this, that will be the same. So if there is a reversible path, and by the way there is a reversible path, then we can just write ds equal to dq upon t, not caring about whether or not that heat is attributed to the reversible pathway or not, because in fact the heat is the same for every single path, because the heat is exactly just the energy that we have took from this surrounding, and that's a state variable, so it's constant. Now, is there really a reversible path? Yes, there is. Suppose your system is like some sort of a gas, like an ideal gas, and it's going through um yeah, so let's just say like this gas is going through isothermal expansion, right, at constant temperature. This guy's having a piston, and that piston is like moving away or whatever, so it requires heat obviously, and that heat is coming from this, right? Now forget about the piston and the gas and everything, because this part is not this reservoir. So what's happening to the reservoir is that there's heat being taken away from the reservoir, and this whole thing is a reversible process. You will have to agree on that. Reversible isobaric process, sorry, isothermal process. You have seen a lot of that stuff. And so what that means is like, yeah, there exists a reversible process where you're taking heat away from this reservoir and it's not saying anything. It's like completely cool with it. And so what that means is you can actually write without any worries ds equal to minus t, so ds surrounding equal to actually I've already written that down, yeah, this quantity. But now remember that this equation is there, so we can write it as minus dE upon t. Cool. And from here we are pretty much done, because just add to this the ds, what was it called, just add to this ds for the system, and what we essentially get is this quantity minus dE upon t plus ds, and that's the entropy change for the whole universe. And so changing this a bit, we can say dE minus dds is minus tds universe, right? And so essentially we have df is equal to minus t ds universe. Yeah, so yeah, that's pretty much it. Yeah, and this is only at constant volume, by the way, constant volume and constant temperature, right? So this is the equation that we have. And once again, some people might object to this whole like thing, because they'll say, oh well, dE minus tds should be 0. It's not. That's not the case. The reason is because the equation is actually dE equal to tds minus pdv plus summation of mu I dni. So this term could be changing for all we know, right? So like there could be chemical reaction going inside, we do not know, and so we cannot just say that this part is the truth. It's wrong. So yeah, that deals with this first question. Actually no, just the first part of the first question. Cool. So yeah, next we want to be doing the Gibbs energy thing. So I'm just going to delete this. So far for the first question we have proved that df is equal to minus t ds universe at constant temperature and volume. Okay, and we also want to be doing something for the Gibbs energy, right? So the Gibbs energy is given by E minus ts plus or I should say E plus PV, or let's just actually just go with enthalpy directly, so just H minus ts. Cool. And H is just E plus PV. Now the good thing about H is that at constant pressure our dH thing can just be written as dE plus pdv, but then you know that dE is just this quantity plus p external dv, actually minus, sorry, plus pdv, right? And in this case what we know is that you know, since it's a quadratic process, we can sort of say that p external dv and pdv will essentially be the same. Yeah, because it has to start and stop. That's kind of the thing. Yeah. Right. Right, so I mean, just have a process where sort of a reversible process, I don't know. You have a process where like your piston just moves a little bit and then it stops, and yeah, that's pretty much the thing. So then the P external is exactly just the pressure, right? Yeah, yeah, right. Because it's essentially like, okay, you know what, actually let's write an even better form for this. Let's just say that in this particular case what you can say is that the work done will always just be minus P external delta V, right? Yeah, and so you can just say dE is, well, the heat that you have put minus this guy, but then this PV changed by how much? It's just exactly P delta V, right? And that's delta H. But then use the fact that, well, P external and P are actually going to be the same because you're doing the quasi-static process, so like you have to stop in between, and so it should be at equilibrium everywhere. That requires P external and P to be the same quantity, and so that implies that delta H is just the heat that you have given it, and so at constant pressure you will have this thing, right? Yeah, right, at constant pressure you will have delta H equal to Q. So now how do we use this fact? We can use this because then we can write Tg is just equal to Th minus, well, temperature is constant, so just Tds, but then dH is just basically Tq, right, which is the heat that we have took. But then once again we know that we can write dq as minus tds surrounding, and so this just becomes like dg is equal to minus tds surrounding minus tds, and so that's just minus t ds universe. And so now we have the other equation as well. Yeah, in fact we probably don't even need to write differentials at this point. We can directly just write the changes and not care about anything. Yeah, that's actually a good idea. So that's pretty much the thing. And over here as well we should just directly be writing that delta F is just minus T delta S universe at constant temperature and volume. And the thing is, like, when we say constant temperature and volume, what we mean is like the final and initial state should have um, constant temperature and volume. Yeah, that's the thing, right? Right. So the final and initial state should have the same temperature volume thing. In between you could probably be having a different sort of process. There's no issue with that because in the end these are like state variables. So yeah, wait a second. Okay, now this isn't a state variable. This is certainly not a state variable. So yeah, it has to be constant temperature and volume throughout. There's no escaping that. Okay, so that's there. Similarly for this as well, you would just have delta G is equal to minus T delta S universe, and this is at constant temperature and pressure. And yeah, by that we mean constant, really just constant. It should be constant throughout. So that's the first part. Yeah, right. So we had to show that for equilibrium your F thing is at minimum, and it's pretty obvious from that, right? That if there is a path between, so like if there is another state, so this is like your current state and there's another state where your F and both of these are like on the same temperature volume, and there is a path with the same temperature volume connecting these two, right? Yeah, right. And yeah, so that there is a quasi-static path that we can use to do that. Then the issue is that the delta S universe for this path, that will be, so delta F is going to be positive. Oh, sorry. Yeah, okay, it should be like on this side, right? So if this is your current state and this is the next state that you want to jump to, and if it just so happens that delta F is going to be negative, and that's messed up because that's saying like delta S universe is positive, and that means that this is a valid path that your system could take and it will take to reach this will give us a bigger entropy of the universe, right? So if it like takes this path, there's no coming back. You can never go back because, yeah, the second law. um, and so this f sorry, this state should in fact be the bottommost point. It cannot be at the top of anything else, because then it's all messed up. So it should be the minimum. And yes, I don't know what variable is on the x-axis, but like whatever. Similarly, something for the delta g as well. Okay. Second, discuss the possibility of a physical system having a negative temperature. Lasers. Yeah, lasers. And that in fact, like any system that has a capped energy, right? So for example, consider a system with let's just say 4 particles. There should be like n particles, but whatever. And these can only have an upspin or a downspin state, and so that the maximum energy is basically like Ni times epsilon, where epsilon is the energy of each of these guys. So if this is like up, it's epsilon, otherwise it's 0, something like that. I don't know, but then this is the maximum energy that you could have, right? So then the number of microstates with so, okay, let's not do that, but just think about it. Then the entropy versus energy graph would look something like that yeah. Okay, I shouldn't be doing this. I should be doing something like this: the entropy versus energy graph. So at a very high energy, that is the maximum energy, there's only like one microstate, so then entropy is like 0, right? Actually, we'll just go with this guy instead, right? So then just have omega equal to 1 at the highest energy, and then at the intermediate energies you have some like bigger omega values. And so what that means is that partial s upon partial e is potentially negative. Yeah, and that actually gives us temperature is negative, right? So in this region particularly, and that's, yeah, this is like really messed up. And at that point thermodynamics like breaks down. But yes, there is certainly a possibility of negative temperature in physical systems, because like things like lasers and other systems with capped energies show this behavior. um, yeah, that's a problem. Anyway, next. Second is like, yeah, there is certainly a possibility. Third is, compare the decrease in the entropy of a reader's brain due to reading of a book with increase in entropy due to illumination by the means of electric light bulbs. So this is completely shitty, because the first entropy increase, sorry, decrease is more like the computer science version of entropy, where you're talking about information and all that, right? And that's completely different from thermodynamic entropy, which deals with particles and all. So you cannot compare these two things, right? It doesn't make sense, so can't compare. And if you think of the thermodynamic entropy change in the in the brain of that guy, you'll understand that entropy of universe did increase, so second law is still followed and all that. So yeah, this is like some really problematic way of looking at entropy, but whatever. Just move on. Like when we say that entropy is related to information, we do not mean it literally, right? Yeah, this is just, I don't know. You're like mixing so many things. You're mixing biology and common sense and computer science. What is this? Like, this just doesn't make sense, right? Entropy, the number, right? The number that tells the entropy of the system, that does increase, because in fact uh, your brain has to have now even more neurons and all that, and since you're just adding material to your brain, that means that the entropy of brain actually increased pretty much, right? And so this whole thing is pretty stupid. Let's just move on. Fourth is right, the principles specific heats Cp and Cv of a substance can be expressed in terms of its temperature, volume, adiabatic compressibility, and isothermal compressibility, and thermal expansivity. Okay, obtain these expressions as follows. What? Oh, so you want to write Cp and Cv in terms of these guys. Okay, so let's just think about it. So you have TdS is equal to CV dt plus alpha t upon kt. So first of all, let's just actually write down the definitions for CV. CV is just partial E by partial T. I think that's the correct thing. Yeah, at constant volume, I suppose. Right? Yeah, I think so. So that's what CV is. Okay, so what are we saying right now? We are saying that TdS is just CV, which is like this quantity. So partial E by partial T at constant volume, that times of dt. Okay, plus uh wow, this is sort of weird, isn't it? ds is equal to this quantity. uh, Fine. So you are actually figuring out how does the entropy change with respect to the temperature and volume, essentially, right? Yeah, okay. So thinking of entropy being a function of temperature and volume, and so you're writing this. So essentially all we have to do is just prove these two equations, that that partial S by partial T at constant volume, that should be equal to 1 upon TCV. If we can prove that, then there's one part that's done, and then you have to prove that partial S upon partial V, in fact, at constant temperature, that would just be equal to alpha upon KT, pretty much. Yeah, so if we can prove these two equations, we'll be done. Because then it's like easy to see that this equation is going to be true. Okay, so let's get to work now. So partial S upon partial T at constant volume, that's 1 upon TCV. Now I'll just write what CV is. It's just partial E by partial T at constant volume. Oh wow, okay, actually makes perfect sense. Yeah, and this equation is like trivially true. Wow. Huh, interesting. Yeah, I mean, this is like trivially true, because all this is just the definition of entropy, basically. Come on, like rearrange this a bit, and what you get is something like T is equal to uh, partial T by partial S at constant volume, and then partial E by partial T at constant volume. But then this whole thing by the chain rule is just partial E by partial S at constant volume, and that's equal to temperature. Wow, that's just a definition of either the temperature or entropy, however you prefer it. But yeah, this is like completely stupid. So this is trivially true. What about this equations? So we just have to put alpha and kt over there. What's alpha? Alpha is this quantity. It's the thermal expansivity, which is 1 upon V partial V by partial T at constant pressure. Okay, and that's divided by KT, which is the isothermal compressibility, which is 1 upon V partial V by partial P. It should be V over there, sorry. At constant what? At constant temperature. Cool. Okay, it's actually negative for some reason. And this one is not negative. What? Yeah, that's weird. Okay, whatever. Just deal with it. So this cancels, and what do you get? You're essentially getting partial V by partial T at constant pressure. Okay. This is slightly weird. Okay, let's just try to write this down. This is equal to minus the partial S upon partial V at constant temperature, and then you just have partial V by partial P. I think I get it. Yeah, so these two are in temperature, right? So all we have to do is just write down this in terms of temperature, right? So how do we start doing that again? Well, we'll have to use the usual thing, which is called the Maxwell relation. Okay, so this one is easy, this one is done. Yeah, sure. We just have to prove this quantity now, and this is going to be easy because we just use Maxwell's relations. So first we'll have to get the Maxwell's relation first. The way this happens is you use the TE value, and that TE is just given as TDS minus PTV, right? And from there you can say that partial T by partial X partial s by partial y minus partial p by partial x partial v by partial y. Did I mess up somewhere? No, most likely I didn't. Yeah, because other terms would just cancel out. There's like commutativity of the, yeah, so that's pretty much the thing. So this is the equation that you'll be using quite a bit. Uh, and so we need to get an equation with temperature and pressure involved somehow, right? So let's just say that y is temperature, and this is supposed to be a constant y, constant x, whatever, but we'll do that. And then x is just the pressure, right? Cool. So this quantity will just be like 1, and this whole thing will just be partial v by partial temperature at constant pressure. Well, this term is gone because partial t by partial p is 0. Yeah. What about this term? Well, this term will be 1, and then x is pressure, so this term is gone. So essentially what you have is like partial s by partial p at constant temperature, that's just partial v by partial t at constant pressure. And the thing that you have is actually this quantity over there. So you can convert that to this thing. So it's just like take that negative, consume it, and now what you have is partial s by partial p at constant temperature. And now this is like trivial. I mean, this is just a chain rule, isn't it? Yeah. So next question. Cool. So fourth one is done. Fifth is, oh, so okay, it's actually just the A part that's done. Wow. It's gonna take quite a bit of time. So A part is done. B, so we have to show that TDS is equal to Cp dt. Oh, come on, will you just not ever stop? So now you want to write, so now you're thinking of entropy as a function of temperature and pressure. Amazing. So now first thing that we want to show is that Cp is just equal to, more like Cp by T, that's equal to partial S by partial T at constant pressure. yes, let's just get started. Wow. So this is actually trivially true because Cp, so this is like 1 upon T over there, and this thing is just like partial E by partial S at constant, sorry, partial T, right, at constant pressure. So this is trivially true. Once again, just using the definition of entropy. Wait, what? No, wait, that doesn't make sense. Cp is, yeah, okay, this is the equation, and what the, at constant pressure, this is the, no, wait, okay, this doesn't make sense. Something is wrong about this. Constant pressure, what? At constant pressure we have to show that, no, but this doesn't make sense. The dp is 0, so then this is equal to TDS. This does not make sense. This should not in fact make sense. This equation is wrong. Yeah, right. This equation is really just wrong. Because now your volume is changing, so you cannot just say this thing. Oh god. Yeah, okay, so the equation they've given is actually wrong, and it's visible. So I'm just gonna move on, I guess. No, but this does not make sense. How could they give an equation which is actually wrong? It doesn't make sense, right? Under constant pressure conditions, what you essentially have is that dE is just equal to, okay, under constant pressure conditions. So let's just think about enthalpy in that case. So then you can say that dH is equal to TDS, right? Under constant pressure situations. So we just have dH upon ds at constant pressure, that's equal to the temperature. Sure. So what's Cp again? Cp is, oh, okay, it's actually correct. It's really, I get it. This should actually be H. So Cp is what? It's the is the amount of heat that you have to put in to change by dt, right, at constant pressure. And we know that at constant pressure heat exchange is just the enthalpy change. So essentially Cp is by definition just partial h upon partial T at constant pressure. So this is trivially true once again. So this part is actually correct. Yeah, fine. So the first part is correct for this thing. Now what we want to show is the non-trivial part, which is that at constant temperature we just have T partial S by partial P is equal to minus alpha T times of V. Yeah, so once again, what's alpha now? And you can just sort of cancel out these T values, so just get this guy. Right, so just got minus V times of alpha. So what's alpha again? Alpha is just 1 upon V partial V by partial T at constant pressure. So this is just this quantity that we want to show. And this shouldn't be hard. Yeah, this shouldn't be hard for you to be doing. So once again, you have the usual thing, partial P by partial X, partial V by partial Y minus T, minus partial T by partial X minus, so the partial S by partial Y. Yes, I sort of introduced a negative sign, but we don't care really. Right, cool. And so now we need to do this with respect to pressure and temperature. So let's just say that X is pressure, Y is temperature. And so what you would have is, well, this is gone. This is just under constant pressure. Yeah, this thing is gone again because X is pressure. Now, and then Y is temperature, right? So this thing is 1 and this thing is just at constant temperature, right? This thing is once again just gone. So what you essentially have is like partial V by partial T at constant pressure is equal to minus partial S by partial P at constant temperature, which is actually this thing. So yeah, and so we are done. These equations are certainly true. Okay, now using these results, you want to prove that okay, Cp minus Cv is this quantity. It's just Tv alpha square upon Kt. Okay. Using these two results, wow, it's a function of constant. Cp minus Cv is just this quantity, huh? Okay. So a constant volume, and that's a constant pressure. Yeah, I am sort of not understanding what's going on. Okay, wait a second. So just think about it. What happens if your entropy is not changing, as in your ds is 0? Then your volume and pressure depend on the temperature essentially, right? Okay, so we can write these equations. What we can say is, and I'm really just going blindly over here, but let's see what happens. So we essentially have Cv is equal to minus alpha T upon Kt, and then you just have partial V or partial T at constant entropy. Yeah, I feel like I'm like stepping into mud right now, but well, let's just see what happens. And then you have fine, just figure it out. Cp is just equal to, yeah, right, it's just equal to positive alpha T times V, and then you got partial P by partial T at constant entropy. Now you somehow want to be using these equations to write down that, prove that equation, right? Upon Kt, that's alpha squared, isn't that right? Come on, think about it. That's the TV term, there's alpha there, that's Kt squared. Yeah, okay, I see where we are heading, but I don't quite like the thing. Fine, just do this thing. So what do you have? You have Cp minus Cv, that's equal to alpha T. Now you're gonna forcefully take out some stuff, right? Okay, so upon Kt, take that out. volume I don't think you should be taking out, so just this is the thing. So just V partial P by partial T at constant entropy, this times of KT, I suppose, this times of KT, right, and then plus, so alpha T is out upon KT is out, so just this quantity partial V by partial T at constant entropy. Cool. Yeah, that's pretty much it. And you should also probably be taking alpha square out, and okay, I'm supposed to be having a V over there. Fine, so okay, let's just figure out what we are supposed to be proving. So I still am not convinced with this, but I'm just gonna run along with it and see what happens. So what you have is that alpha V, yeah, that quantity should be equal to this quantity. So just VKT partial P by partial T at constant entropy plus partial V by partial T at constant entropy. Okay, cool. So what does this give us though? What's KT? KT is at constant temperature, not good. We'll have to somehow figure out how to convert it to constant entropy, right? Yeah. You can't, by the way. Yeah, that's actually not possible. What is alpha again? Alpha is just this quantity. Okay, so at least alpha V is something that we can use. So alpha V is just partial V by partial T at constant pressure. Yeah, right. And that's equal to this quantity. KT is just minus, so VKT in fact, this is just minus partial V by partial P at constant temperature, partial V by partial T at constant entropy, plus partial V by partial T at constant entropy. Amazing, that's the thing. Now how can we use this? Yeah, this is problematic. So you can write everything in terms of entropy over there. Yeah, that makes sense. That will be at constant temperature, and that's gonna hopefully clear out some stuff. Who am I kidding? That's not gonna clear out anything. It's at constant pressure. It says constant temperature, constant temperature. Oh wait, I see a path. So I'm just gonna copy this. So essentially we want to prove this thing, right? Okay, cool. So notice that over here you have temperature, over here you have temperature, over here you have temperature already, and this thing can also be converted to something with constant temperature. So you just want to convert everything to constant temperature and you'll be done. Nice. I see. That's actually going to be useful. Cool. So let's just start. Convert this to a constant temperature situation. How is that going to happen? So once again you have the usual equation, partial s upon partial x partial. Yeah, I've got, yeah, I'm actually sort of tired. It should be t over there. I'll just start with p or whatever. Yeah, and now we just need these equations. So first partial v by partial t at constant pressure. How are you gonna get that? So you just put x equal to t and y equal to p, and what do you get? Well, this guy cancels, so just have partial v by partial p at constant temperature, minus this guy is there, so minus, oh wait, something is messed up. Right, okay, this actually just cancels because x equal to t, so this is gonna go down, and you just got minus partial s upon partial y is p. Okay, and that's equal to, this thing is so partial v by partial t at constant pressure, right? So you can write this quantity as that, so I'm just gonna replace it with this. So this is just minus partial s by partial p at constant temperature, so that part is done. So we can just delete this whole thing now. Right. Next, we want to figure out something about this guy. So partially upon partial T at constant entropy. So we put x equal to temperature, y equal to entropy, and see what we get. So putting x equal to temperature. Oh, that's problematic, isn't it? Let's just see what happens. In fact, let's not do that part first. Let's actually do this part. Okay, no, actually let's try it out. Who knows? Maybe you will get something nice. I see, this is sort of troublesome, isn't it? Yeah. So both terms will be there now, unfortunately. Both temperature and entropy. Oh, that isn't good. This is certainly not good. I don't quite like that. There's got to be some other way. Okay, let's try to figure out what this term is gonna be. This partial p by partial t at constant entropy term. So just say x equal to t and y equal to s. Let's see what happens. Wait, but that's... Oh yeah, okay, right. That's exactly what we just did. Not helps. Doesn't help, right? So you can't really just deal with that like that. Can we deal with something that's sort of easier to deal with? Hopefully. I don't know. That's already at constant temperature. Why do I feel this is not going well? Yeah, this whole scheme is not working out. How about I multiply by partial t by partial p? Yeah, that's surely going to bring out some stuff, right? Yeah. So if I do that, what do I get? Oh, I'm just gonna get something problematic, isn't that right? Yeah, I need to apply the chain rule somehow. Apply the chain rule. Partial P by partial T. So with pressure and entropy, this would work. P, P and T, right? P, T and S is not actually useful. But how do you even get rid of that? Yeah, you probably can't. Wait a second. Entropy, pressure, temperature. Oh. So you just need another thing with the pressure term in there. Okay, cool. I see. Although it's not very useful in the end. I'm just thinking we should just revert back to the original one. Should I just give up on this thing? It's not a very good idea. Okay, so since we can't be converting it directly, there's got to be some other way. It's like pressure and entropy. There's temperature and entropy. Yeah, so temperature and entropy is not a very good idea. Temperature and entropy. That's pressure versus volume. Interesting. And that's at constant temperature, isn't it? Hey, so if I just sort of, exchange some terms everywhere, things might just become it just becomes slightly better, right? I see. Yeah, I see the truth in that. So let's try that out. Who knows? Things might just get better. So if I just take the reciprocal of this guy everywhere, I'll just get 1 is equal to partial V by partial P at constant temperature. Yeah, okay, I thought so. Something might just give way to partial T at constant entropy, and then minus partial P by partial S at constant temperature, and then partial V by partial T at constant entropy. Interesting. So this whole thing can be written so without the partial p involved. I see. This is exactly the identity that we're looking for. um, yeah, and this I think is actually doable, and this probably is in fact very doable. Okay, cool. Yes, obviously it is. It is in fact. So just move that term there or something, isn't it right? Yeah, okay. So what you'll just have is something like partial p upon partial s at constant temperature, partial v by partial t at constant entropy, is equal to, that's over there, partial v, so partial p in fact, partial p upon partial t at constant entropy, partial v by partial s at constant temperature minus 1. And guess what? Yeah, this is trivially true because we have been dealing with these sort of equations for a long time at this point. I should also like just write it like this, and then now it like makes sense. Just put x equal to s, y equal to t, and now you can see why this is true, right? Yeah, yeah, this makes sense. X equal to s, y equal to t. First there's like t and then there's s. So yeah, this is true, obviously. And so there it is. We have proved that this equation is also true. Alright, let's go to the D part. Express Cp and Cv in terms of temperature, volume, alpha, Kt, Ks. Didn't we just do that? We wrote Cp minus Cv as Tv alpha square upon Kt, right? So we in fact didn't even use Ks, and so we are done, right? Oh no, okay, wait. We wrote Cv minus Cv in terms of that. I get it. This is going to be hard. Yeah. Okay, just think about it. How are you going to write this? Temperature, volume, alpha, Kt and Ks. So if we were just given the equation, it would be so much easier to write, but now it's not the case. So even if like we are able to write one of these equations, we are essentially done, right? Okay, so we could start with this guy. Cv is just T partial S upon partial T at constant volume, and so now we just need to convert it to something that we could use. Yeah, so this is gonna require lots of space. Let's just go to the next page. So what we want to do is use this equation. Cv is equal to T partial S upon partial T at constant volume, and also these equations. So temperature we already have, we know that. Alpha thing is just the 1 upon v partial p by partial, I think it's just partial p by partial t, right, at constant pressure. Was that the case? Yeah, that's alpha. The Kt thing is just 1 upon v partial v by constant temperature, and then Ks is just 1 upon v constant entropy, right? Yeah, cool. And how do we use that to write down this equation? That's the question. Cool. Think about it. Partial A, partial P at constant temperature, pressure, entropy. Interesting. We're simply converting it to another equation. Yeah, sure. It's pressure and there is entropy. Anything that is common between each of these. There's got to be something that's common, right? Let's just try to convert everything in terms of entropy and volume. So this will be converted to something that's having volume over there, right? Okay, let's just say temperature and volume, that's better. So this will be converted to something with, okay, that's actually not better. Temperature and volume. Oh, this is already temperature, isn't that right? Yeah. It's constant pressure. Okay. That's problematic. This is something we don't want to be dealing with. Okay, so we need to sort of change a lot of things now, but let's just get started. Oh, this should also be negative, right? Yeah, right. Cool. So let's get started now. So we just want to write everything in terms of volume and temperature. So first we'll just get this term partial V or partial V at constant temperature. That's just equal to minus 1 upon V kT, right? Something that we'll be using later on. Then this term as well, we want to be writing in terms of volume and temperature, right? So just partial V or partial V at constant entropy is just minus 1 upon V Ks, obviously. But this will be able to write differently, I think so. So volume and entropy, yeah, this is a good combination. So just have partial V or partial X. Let's just say that X thing is now volume, okay? So partial V by partial Y, partial S, what? Okay, this is actually 0, right? Yeah, okay, this is 0. So minus TD, so partial T by partial X, so just partial T by partial V, and then partial S by partial Y, that's just 1. Okay, so this is the thing, and that's equal to oh, this is actually confusing. Okay, so upon wow, okay, I should actually write this down, who knows. So partial P by partial X, partial V by partial Y minus partial T by partial X, partial S by partial Y. X is just the volume, Y is just the entropy. So since X is the volume, Y is the entropy, this term is gonna be just gone, so you can't be dealing with that anymore. Okay, amazing. Now what about this term? Okay, so this will just be minus partial T by partial volume at constant entropy. That would just be equal to, so from there you have partial P by partial Y, partial U by partial X. Well, that's just 1, so that's just partial U by partial volume, yes, at constant entropy. So you got one term at least. Something's messed up. Something is certainly messed up. Oh, this shouldn't be the case. This should be partial P by partial S at constant volume, right? So that's one equation that we have, not useful right now. Okay, yeah, that didn't really work out, did it? It didn't. Oof. So okay, that didn't work. Now what do we do? Yeah, but we certainly need something like that, right? So partial P by partial V at constant entropy. Constant entropy. But okay, it's just impossible to be doing that, right? Yeah, it is. Fine. Now this is not making sense. You have volume and temperature and come on, at constant entropy there's only one term which is at constant entropy, which is partial V. So the other way around is, well, to transform it with respect to pressure and entropy, and I don't have very high hopes for that. Yeah, or at least you are going to get that, in fact. Okay, let's just try that instead. So let's just say that, oh wow, that wasn't good. So let's just say X is pressure instead, and so you just have something like partial V by partial entropy at constant pressure, that's just equal to, so this is partial T by partial X is pressure, this thing is the partial V by partial pressure. Wow, at constant, that didn't work out, certainly didn't. So pressure and entropy certainly didn't work out, did it? No, I thought you would get something nice, you didn't. Why? What the? Why is just the entropy? Excess the pressure. Yeah. So why did it not work out then? Entropy and pressure. So what if X was entropy and Y was pressure? Well, if Y was pressure, then okay, then this would be this would be a complicated equation, which we're not really interested in. Okay, apparently you can't have partial V by partial P. Yeah, that's a bad scenario. Right. It makes sense. That's actually a bad scenario. You should not be thinking of it like that. So you will need to split it into two different things. Isn't that right? Ah. Oh, this is much more complicated than what I thought it will be. Wow. It's partial S by partial T. Come on, think about it. What can we do? So you got volume and temperature. Okay, that's everything with volume and temperature. Interesting. So if I switch this, because temperature and entropy together are sort of incompatible. So let's just say I switch this. I put pressure over there. Then it should be like partially or partial temperature constant volume, right? Sorry. So now are these doable? I think sort of. So entropy and volume can be exchanged, and who knows, that might give us something like that. Okay, it won't. The pressure term, that's not a good idea. Yeah. But what else do you even have? You don't have anything else. Okay. Yeah, I mean, temperature is used up, volume is used up, entropy is used up. Any other variable that you want to include, that has to be pressure. Okay. Not good at all. Think about it. So what about changing this into pressure over there? Yeah, that would probably work. So yeah, so instead of entropy you would have the temperature term. I see. So these two terms can sort of be patched up. That makes sense. So you can change the pressure and volume term, and that's going to give us the reciprocal of that apparently. Cool. Okay, that's one thing that you can sort of use. So that's one good equation. So you just want partial S by partial P at constant. Well, okay. And by the way, these equations that we're making, we should sort of not be erasing them. Fine. So now let's just use X equal to pressure and Y equal to volume. That's going to be a bad equation. I sort of think so. Yeah, okay. It's going to give us that 1 and all that stuff. Not a good idea. Why is this so weird? What about CP instead? Yeah, that would be S and V, and that's at constant pressure. So you still have to use pressure and volume. Damn it. Not good. So it's temperature over there. At constant entropy. It's got to be a different way. There has to be a different way than this. What about volume and entropy? Just trying out every single combination. Yeah, that way you'll get at least one thing that you could sort of be using, right? Yeah, so use volume and entropy. Switch that up. So then you will get a subscript of entropy. You will have volume. Okay, that exactly matches up with this quantity, but then the pressure is not there. You should not have pressure over there. It should be something else. Okay. So what else will be there? It will be temperature, right? That will be temperature. So this will be partial T, and then you just got partial T by partial P at constant entropy. You will need this extra term, but how do you get this extra term? Because your entropy term is like used up, so Yeah, that's not very good. Ah. What about the partial P by partial T term? Okay, we're just doing it without a plan, are we? Yeah, we are certainly doing it without a plan. We won't be able to make any progress from this point. But once again, the whole situation is either switch with pressure or with entropy. And switching with pressure is a bizarre and problematic scenario. Okay, let's just forget about this term for a while and just focus on this term instead. So we could once again just switch with pressure, or you could switch with temperature, and that will hopefully produce something nice. But it will erase the cosmic volume situation that you have, right? Yeah, right. So if you change with temperature, what will you get? You'll get, instead of pressure, you'll be having entropy. But there's no sign of entropy over there. That isn't good. Yeah, that is not good. So what about changing with pressure? If you change with pressure, things will be problematic. I wish there was a better way than this. There has to be a more systematic way, right? You just get volume and pressure in that case. So if I actually used CP instead, right? So if I use CP as something like this, would that be better? So now when you change with entropy, you'll get a partial P over there, and instead of volume, you will be having something else, right? That's still bizarre for me. Yeah, okay. So we'll probably still be getting something problematic. You sort of can't be changing with that. Huh. So in both scenarios, it's just messed up. You're bound to be getting that 1 plus term. Right. There is no escaping it. Fine. Whatever. Okay, what about this term? Will it be sort of better than the last time? I actually don't know. Come on. Think. Why can't you think right now? Convert this to entropy. That will be having pressure term over there. You can't change with. Okay. Okay, that's not good. uh Shit. Okay, that is certainly not good. So you'll have temperature, we'll have this change with pressure, and so it's gonna be like, instead of V you will have P. What? No. Partial V with respect to P. How does that even make sense? No, you will probably never get a term like that in the first place. It's just impossible, right? Yeah. Our best bet is in fact to just have pressure and volume. At least those terms are compatible. Right. Wait, what was the thing initially? It's just partial S upon partial T. Right, okay, that was certainly incompatible. So, yeah, okay. That's just our best bet. Let's do the thing. Yeah, it's gonna be very problematic. But we have to do it if we have to do it. So, yeah. Shouldn't there be some way of doing this? Express CP and CV in terms of that. Okay, so we have to find the equation. Just do it. Cool. So first we'll figure out what this term is. Yeah. So we have this constant entropy term. Okay. So you could switch with the entropy stuff. That's one way of dealing with this. But that isn't going to be like really useful though. So probably not a good idea. This is like partial P by partial V under constant entropy, right? Okay. So yeah, we'll just have to switch this up with volume and see what happens. And over here as well, we'll switch that up with volume and see what happens. So put that over there, just get partial T by partial. Actually, no, that's probably not a good idea. Just keep it like that. Awesome. So yeah, just switch this with volume. Let's see. So you're going to put x equal to v and y equal to p, right? Or the opposite, doesn't even make any difference. So what do you get? You get something like, so it's 1. This stuff is just minus partial t by partial p constant volume partial s by partial v at constant pressure, that's equal to partial t by partial volume at constant pressure. Wow, that is not useful at all. That's problematic again, but hopefully gives us what we want, right? We want this term partial s by partial v at constant pressure, and that is something we are certainly getting. So it just needs to be multiplied with partial t by partial p at constant volume. Yes, partial t by partial v at constant volume, just the complete opposite of that. That's what they've given us. Not a good idea. So what they have given is like partial v or partial t at constant pressure, huh? Oh look, okay, this term is there actually, so you can multiply this out and you will get something like partial t by partial v at constant pressure minus partial s by partial p at constant volume. That's equal to this term. Wait a second. Okay, I'm like just getting a really bad feeling from this, but let's see what we get. So now you multiplied by this thing, right? So partial p by partial t at constant pressure and partial p by partial, so yeah, okay, this term is going to be multiplied by that partial p by partial t at constant volume. Amazing. Interesting. Wait a second. What? No, wait. What the? This is very weird actually. That's partial p by partial. Oh, this is making me uncomfortable. God, what is this? Okay, so this is one of these terms. Sure, you can write it exactly like that. Fine. I don't know. This term though, partial s upon partial t at constant volume, we have seen this, right? Oh, it's the CV term. Yeah, obviously. That's like from that equation, that CP minus CV thing. So we're going towards that for some reason. I don't like that. Okay. Now, how do we deal with this stuff? Okay, so at least this term is familiar, isn't it? Yeah, okay, it is. Oh no, we are just deriving that equation again. Not a good idea. This is hopefully the best scenario over there. Oh, come on. But that's once again the same scenario, so like any hope of solving that would be the same as any hope of solving this. So yeah. Yep. Essentially we just want to be simplifying CV in that case. So this whole thing is just problematic. You are not going to get anything out of it. Okay, what's this? What's the other scenario though? So you got partial S by partial P in that case at constant volume, and then partial P upon partial T at constant pressure. Sorry, at constant volume again. Wow. Nope. This is just really problematic. I don't know. I should move on. This is just I just don't know, and that's why it's not working. I don't think there's a trivial way to be just solving this. Express Cp and Cv in terms of Kv, alpha, Kt, and Ks. So you have one equation giving us Cp minus Cv. If you just had some other equation giving us something slightly different, you would be done. Gamma, right? What's Cp upon Cv, right? So it's like partial. So it's just basically just partial T at constant pressure, partial T by partial S at constant volume. Interesting. Okay, so how is this gonna help us though? It probably won't. Yeah, right. At least temperature and pressure are compatible. Entropy and this guy probably also compatible. So if we can somehow prove that this thing is in some way related to that, we'll be done again. If we can prove that. Like if you know what CPCV is, you probably also know what CP upon CV is. Um, so how about we try doing this? So instead of pressure and okay, let's just actually bring everything in terms of temperature. It will help us hopefully. Okay, it won't. It just won't help us. God, this is not good. So let's just try eliminating entropy from there, right? So then we switch this temperature and pressure, and that eliminates the entropy, I suppose. Oh, by the way, this temperature is already like it's problematic, isn't it? Right. Ah, yeah, you will actually never get a term like in the first place. Wow. So now what? We'll have to do this thing. Yeah, this is not good. Certainly not good. Constant what? Constant. Why is this so complicated? Okay, so what things do we actually have? We have one term with this constant entropy. Okay, so maybe we can switch these things. So constant entropy and oh wait, that actually works. If we switch this, we'll probably also get a volume term, right? So that's one way we could solve that. Okay, let's actually try that out. So you got partial S upon partial T at this is not a good idea, right? I mean, you can't actually switch that up because the temperature term is incompatible in the end, right? Yeah, it is incompatible, so you will have to do something else. This too, it's just incompatible, so you'll have to do something else. So now what do we do after this point? We are just always stuck at this stuff, isn't that right? Just copy that and see if like something makes sense. So you want to simplify this using these equations. Yeah, just as messed up as it was earlier. uh okay, partial V by partial T at constant pressure. Hey, that's one term we see. Okay, so this thing is just alpha V essentially, right? Okay, that's one term gone. This thing is just foggy. Okay, cool. Fine. Partial P or partial S. Volume. The constant volume term is not there, so there's no way to be changing that. Oh wait, okay, so from here you can sort of convert to this, I think so. Again, right? Right, so what do you have? You have entropy over there, you have pressure and volume. You're not changing that. Wait, what? Does this even make sense though? Pressure and volume. No, that doesn't make sense. So instead entropy and volume is better. Yeah, so you will get something like that. Okay, let's just try to do this thing. Let's just try to multiply by that. Who knows, you might just get something good. Wait, I see something. Partial S or partial V at constant pressure, partial P by partial S at constant volume. If you have another term, then things might just cancel out, right? So the other term that you need is one at constant entropy, which is interesting. So if we bring both of these to constant entropy, you might just get this term. In fact, you will get this term. Let's actually try it out. Convert both of these to constant entropy situations. So just switch S and P and switch P and S, right? And then things will make sense because it's just the chain rule over there. Yeah. Constant volume. Yeah, hopefully it makes sense. Let's try to figure it out. Okay, let's see. So what do we have? We have that. So just switching what? Just switching P and S and what? This is V and S. Cool. So we got partial P by partial S, partial P by partial partial V by partial V minus partial T by partial S by partial V is equal to partial P by partial V V by partial S minus partial. Yes, this is tedious. I don't want to be doing this ever again. So you just get this equation: partial P by partial S at constant volume is equal to minus partial T by partial V at constant entropy. Cool. Yeah, so that's the reciprocal of this, right? Cool. So you will just basically be having partial V by partial T at constant entropy. That the negative of that, in fact, that's what this term will be. Okay, so just replace it with that instead. Negative partial V by partial T. At constant entropy. What about this term? Partial P by partial S, right? So just put a P over there rather than V. So what do you get? So what you get is something like okay. So this term is just gone. What about this term? So it's with respect to S and P, right? Okay, cool. S and P. Why does this look so weird? Oh, this term is gone, this term is gone. So these two remain. So you just get partial V by partial S. That's equal to partial T by partial P. Once again at constant pressure, at constant entropy. So you already have this term somewhere. Partial V by partial S. Okay, wait, no, you don't. Wait, why do you not have that term? What you have is what? That's entropy and volume. Okay, that doesn't even make sense any. Like, uh, but we just did entropy and volume. How did you? Oh, that won't make sense, huh? Sorry, you're supposed to do pressure and volume. What am I doing? No, no, this doesn't make sense. You can't be doing pressure and volume. That won't make sense, in fact. Okay. I guess it's a good time to take a break because this is just getting too much. So I'll see you guys in the next video. Bye.